Hello, everybody. My name is Mironchenko. Welcome to my talk on criteria for input-to-state stability of time delay systems. This is a joint work with Fabian Wirth, Antoine Chaillet, and Lucas Brivadis. In this talk, we will consider nonlinear time delay systems of this form, where xt is the state of the system at time t, so it is a continuous function defined on interval t minus theta to t, where theta is the fixed maximal time delay, and u is an external input, which we assume to be essentially bounded and Lebesgue measurable function. Also, we assume that f is continuous in both variables, f of 0 is 0, and f is Lipschitz with respect to the first variable on bounded balls. Under these assumptions, as usual, we obtain that for any initial condition and any input, there is a unique maximal solution of time delay system, which does not have to be globally defined. However, since we are interested in analyzing stability of the systems, we will need also to study the global existence of solutions. And so we define two notions. We will call a system forward complete if the maximal solution corresponding to any initial condition and any input exists globally. And we say that our system has bounded reachability sets if it is forward complete, and in addition, if the flow map maps bounded sets into bounded sets. The distinction between these notions is subtle but very important. Note that this BRS property can be understood as a bridge between well-posedness theory, which is interested purely in existence uniqueness of solutions and does not give any bounds, and stability theory, which is interested in global bounds, global and time bounds in solutions. BRS gives us bounds, but only on finite time intervals. For ODEs, these two concepts are equivalent under our assumptions on F. And also they're equivalent for linear infinite dimensional systems in Banach spaces. However, if infinite dimensionality with nonlinearity play together, then these two concepts are no more equivalent and BRS becomes significantly stronger. And there are such examples for infinite networks of ODE systems in particular. It is interesting for us, however, whether these two concepts are equivalent for time delay systems. Before we answer that, let me recall that a time delay system is called uniformly globally asymptotically stable at 0 if for a 0 input the norm of the trajectory can be upper bounded by a KL function depending on the norm of the state and time. So this function increases in the first argument and decreases to 0 in time. Okay. And now here comes the answer, which was given in this year by Mansilla Aguilar and Hernan Haimovich. They considered time delay systems under our assumptions on F and also with a state space as a space of continuous functions, and they construct a time delay system with three modes, which is forward complete, globally asymptotically stable, locally exponentially stable, and also uniformly globally attractive. So this means that initial conditions starting in bounded balls, they converge to 0 with the same speed on bounded balls. At the same time, in spite of all these nice properties, the system does not have bounded reachability sets, and so it is not uniformly globally asymptotically stable. Moreover, if we do not assume uniform global attractivity, but merely these three properties, then the system does not have to be a BRS, but also it does not have to be uniformly globally attractive. And this was given in another counterexample constructed on the base of that previous example by Mansilla Aguilar and Haimovich in this paper. So basically these two examples, they show that there is a significant difference between forward completeness and boundedness of reachability sets. And this is precise, and BRS property is much more useful for stability analysis, as we will see next. So now we go to the, okay. Also, let me recall that all what we have done previously, all these examples, they were about systems with a state space of continuous functions. If we can also change the state space and consider time delay systems on a Sobolev space, which consists of continuous functions with some additional regularity. And in this case, forward completeness becomes equivalent to BRS. So taking better state space results in getting this equivalence. What is interesting, that if we take the state space worse, L infinity space, then forward completeness is again equivalent to BRS. And basically it seems that failing this equivalence is a peculiarity of continuous functions. Okay, now having understood the relation between forward completeness and BRS, we proceed to the main topic, to ISS analysis. We call our time delay system input to state stable, or shortly ISS, if the norm of the trajectory is upper bounded by a sum of two terms. The first is the transient term, which we have seen in UGuess definition, and another term is a so-called gain, and it describes the asymptotic deviation of the system from the origin. So if U is identically zero, the system becomes UGuess, and if U is non-zero, then the trajectory converges to the ball with the radius gamma of norm of U around the origin. This feature that ISS unifies both stability with respect to initial condition and robustness with respect to inputs has made ISS dominating stability paradigm in nonlinear control. And it is essential for robust control and robust observation of nonlinear systems, for analysis and control of large-scale networks and other areas. So there are several works, books, and surveys devoted to ISS, including this very recent survey by Chaillet, Karafilis, Pepe, and Wang on time delay, ISS of delay systems. So the ISS theory for delay systems has been started with the pioneering work by Andrew Thiel in 1998, and afterwards, since that, we have already a rich palette of tools which can be used for ISS analysis, such as Lyapunov-Krasovsky and Lyapunov-Razumikhin functions. We have converse Lyapunov-Krasovsky results. We have small gain results, linear, nonlinear Hallan inequalities, and other tools. Nevertheless, there are several fundamental questions which are still not understood. One of them is, what are tight characterizations of ISS? So what actually ISS means? And another one, how to define Lyapunov-Krasovsky functionals in a most useful way. And today I would like to answer this first question. And on the second question, I will talk a bit on Friday. So to characterize ISS, we need one more property, which is called uniform limit property. It states that a system has this property if there is a gain gamma such that for any radius r, there is a uniform time, so that if we start in a ball with radius r and apply inputs bounded in magnitude by r, then within this time we reach epsilon neighborhood of these balls with radius gamma of norm of u. So this holds. Okay? So basically this means that starting from certainly from our initial condition, we necessarily reach this neighborhood around this ball. It does not say that we stay in this neighborhood. We may then deviate out of it. So it's kind of butterfly swimming pattern. So we dive into the water or our epsilon neighborhood, and then we step away, and then we dive again, and so on. So this is kind of a pattern. It is related to so-called weak attractivity of dynamical systems. Besides this uniform limit property, it makes sense to introduce strong limit and non-uniform limit properties. They have the same idea. The only difference is the dependence of this time within which we are reaching these neighborhoods. For uniform limit property, this time depends only on the norm of state and norm of the input. For strong limit property, it depends on the norm of the input, but can be different for states with the same norm. And for limit, it depends on x and u, and it is completely non-uniform. So clearly, uniform limit is the strongest one, and this is the weakest one of all. Interestingly, for ordinary differential equations, all these concepts are equivalent. It was shown in this IEEE tech paper where the ISS characterizations for infinite dimensional systems were proved, and it is strongly based on the seminal work by Zonta and Wang. And now here comes our first result for delay systems in this respect. Namely, we have shown that if we assume boundedness of reachability sets, then strong limit is equivalent to uniform limit property. We have to assume BRS. Without this assumption, strong limit is considerably weaker than uniform limit. At the same time, we still don't know whether limit property implies strong limit property for BRS systems. And now we proceed to our main result. We want to have a so-called ISS superposition theorem for time delay systems. Well, we have already one of such results, actually. We have a general characterizations of ISS for a broad class of infinite dimensional systems, including time delay systems and many classes of PDEs, infinite ODEs, etc. It states that system is ISS if and only if it has BRS property, uniform limit property, and is uniformly locally stable. But this is a very general result for a very general class of systems. It is tight within that broad class of systems, but for special types of control systems, it can be relaxed. In particular, in the original work by Zonta and Wang, where they have studied this problem for ODEs, they have shown that for ODEs, ISS is equivalent to forward completeness, non-uniform limit property, and local stability of an undisturbed system. So for ODEs, we can relax any of these properties, actually. The question is what to do about time delay systems. And here is our result. We have shown that ISS is equivalent to boundedness of reachability sets, strong limit property, and local stability of undisturbed system. So we can't relax BRS to merely forward completeness due to counterexamples mentioned earlier. Here we have reached the best possible result, and the only thing where we still don't know whether it's a final or not, whether we can relax strong limit property to just a limit property. We don't know that, but this is what we have right now. And it is mentioned in TNS, and we are working now on a journal version of this paper. So, a proof. Strong limit, as we have seen, strong limit is equivalent to uniform limit since we assume BRS. So we have this result. Next, one can show using uniform limit property that our system will be undisturbed system is uniformly globally asymptotically stable. Then using local robustness of UGAS, due to this paper by Palumbo, Pepe, Panunzi, and De Gaetano, our system is locally stable. And then we just apply the general characterization of ISS for infinite dimensional systems, and we get the result. So the proof is easy as long as we know all these lemmas. Why do we need such results? Well, ISS superposition theorem can be understood as a meta tool which helps to develop other tools. It was essential for non-cursive ISS Lyapunov theory, for development of small gain results for finite and infinite networks, to relate ISS and integral versions of ISS, etc. And as I will tell on Friday, it's important also for Lyapunov-Krasovsky theory for time delay systems. So now we come to the last slide. We have analyzed nonlinear delay systems with Lipschitz nonlinearities. We have shown or mentioned that if we take continuous function as a state space, then forward completeness is weaker than boundedness of reachability sets. And using this stronger property, we can characterize ISS as BRS plus strong limit property and some stability at equilibrium. So the results which I have presented can be found in these works, and thanks a lot for your attention. I'm looking forward to your questions.